Hi everyone. We just happened to switch the order of presentations, and then I was supposed to give a talk at the 1:15, but I'm going to take over this time slot to discuss about my presentation on quantum error mitigation by machine learning, right? So again, I'm June-Koo Rhee, also known as Kevin. And this work was done with collaboration with Dr. Chang-Jun Kim, who just passed the defense yesterday, and also Dr. Daniel Park, who is the organizer of this symposium. And I'm affiliated with the KAIST ITRC of quantum computing for AI, and also School of Electrical Engineering and the Institute. And there is a new startup company called Qnova, and this one will appear soon in the world. Okay. Anyway, so this work is basically based on Dr. Chang-Jun Kim's thesis work with me, and I'm going to give a presentation on this one. So as an introduction. So let's consider we have the quantum computer, which is basically a NISQ computer, and NISQ computer comes along with the error in computation, right? And then the problem is the error is kind of the depreciating all the value of the quantum computation, and we want to be able to reduce the error in the outcome measurement. And that can be done in several methods, but what we are going to do is trying to reduce or mitigate amount of error in the final outcomes after the computation. So this is a problem size of big over 2 to the n, because the where n is the number of qubits, and because the complexity of the quantum computing has 2 to the n, right? However, if we just try to use classical machine to understand what's happening with here, it may not be efficient enough, because the classical machines can have only the computational complexity of big over n. So so the basic question is, we know that fixing the problem of the QPU, is going to be anyway a very complex problem. And what we are going to try is, fixing the QPU problem with another QPUs will have another QPU problem. So we try to fix that with the classical machines, which is the conventional, the machine learning algorithms. So we want to analyze the behavior of one unitary transformation, right? And also the behavior of multi-unitary transformations using classical machine learning, okay? So in this cartoon, this I'm going to try to show how big challenge this is, right? So David is trying to fight against or fix problems with Goliath, right? With this relatively simple classical machine, and try to understand the problem that you have with the Goliath, right? And we investigate how this one can be done, or this is going to be really work out. So the contents of my talk is following. So I'm going to introduce about the quantum circuit error mitigation, and also so in this stage we just explore some possible solutions, and it is followed by another discussion about the quantum error mitigation that provides a scalability, where we try to reduce the size of training and introduce the convolutional the network, neural network that also provides a pretty good the solution. I mean, pretty good performance as with the previous one. Okay. So I'm going to discuss these two pieces of work. Why do we discuss about error mitigation? Is following. So the error problems can be fixed with quantum error correction to provide error-free logical qubits. However, this is a very complex problem. Probably you will need several supercomputers to fix the error problem of the one QPU. So instead of doing this complex problem, so we can also consider error mitigation. That means we don't understand the nature of error, completely. However, what we can do is we just to know the pattern of error. So we can try to partially fix the error in the pattern with the pattern, right? So this is the scope, the basic objective of our work. So this paper investigates the quantum error mitigation with the NISQ computers. So motivations are like this one. So we have the multi-qubit system with the unitary operations, and each unitary operation comes with some error. So we call that as an error channel. And then as it passes on, the probability of having error or not produces the very complex trajectory of the errors, right? So the number of terms are increasing exponentially. So it is not easy to understand the whole problem here. And we try to introduce machine learning to find out the patterns in this dynamics with the quantum computers. So when you have error in a circuit, for example, this one is produce a very simple state like 1 0, and then after the at the end of it, this state should have like a 0 0 plus 1 0 state. And however, if there is an error in this circuit, for example, then there can be other states that is not supposed to show up, which are error states, right? And then the gates can introduce errors, and also the measurement can introduce errors. So NISQ machines, we can classify two errors separately. One is a gate error, the other is measurement error. At the moment, if you run, for example, the IBM Q machines, you can mitigate the errors from the measurement. So the KAIST error correction error mitigation API provides the reduction of the errors. Okay. However, the gate error is not handled in KAIST error model. Anyway, so we end up with some error probably the error states like this one. So probability of measuring 0 0 and 1 0 is the major part of the state, but we have error state like 0 1 state and 1 1 state with a low probability, but still this is an error. So we want to reduce the amount of error that appears in the error states. And the quantum error correction can be applied with some additional redundant qubits. So we can introduce, the coding with some redundancy, and then we can provide, more error. I mean, we can provide the error corrections. So this one requires more resource, quantum resource, which is expensive, and also the correction algorithm becomes very complex. However, error mitigation, we just run the original circuit as is, and then error mitigation is applied in the classical, domain. So for example, when you have a probability error like that, these two are error state, we apply the error mitigation by use of machine learning. Then we can potentially reduce these errors and reduce error state probability and increase the true state and answer state probability, like this one. In ideal case, we can do this one. However, that does not really happen as we studied in our experiments. So this is an example of the NISQ machines. Okay, so for example, the IBM 16 qubit Melbourne system shows some the NISQ machine performance, right? So on a blue side, the single qubit case has low errors, and on the purple side it has a higher errors, right? Also, in the 2 qubit case, that is represented here as the edges of the graph, has a certain error probability distributions, like the CNAT error rate is shown here. So these can introduce a complex error in the system. So altogether, the question becomes, if we can train a classical machine with this kind of error problem, right? So initial state is given, for example, then the original calculation should be done like U1, U2, and UK. And then we do measurement and probabilities measured, and we construct the answers, right? But with error, we have measurement with the error, and then the result will have error probability. So if we compare these two numbers, then we can find out the error. So this is the state with error, and this is the state with no error, and the difference becomes error. And if you just look at the amount of error, for example, in this kind of the test run with a Melbourne machine, then we can find out the ideally we should not have any probability on these two states, but we have this kind of errors, and we want to mitigate to eliminate the errors in the result. So what we have done is we have quantum circuit, and we have machine learning, the algorithms that is done with the classical computer. So we just try to train this machine with many circuit examples. So these circuit examples produces training samples, right? So these are trained, and then later we test with the other circuit to see if the error can be mitigated by this machines. And there are two kinds of experiments. One is just a simulation by the state vector machine. So this is the quantum circuits are calculated with the classical method, right? And the other is the experiment. The experiment is done with the IBM Q machines, and this one has more complex errors. And with the simulation, we employed the the error models provided by the KIST AER error model. So this one tells you about the how the density matrix of the two-qubit system will have errors. Okay, but because of time limit, I'm going to skip details of discussions. And another one is the density matrix for two-qubit error is depicted here. So basically, we can consider some decoherence errors. One of them is a depolarization error. And if you have two qubit, we can have some analytical form, but this is just an analytical form that doesn't tell all the complex nature of the classical and the quantum computation. So as you can see here, we can also introduce the artificial neural network to learn about the model of errors. Okay, and then what is done is like this. So we have, for example, random circuits, right? We are teaching the neural network with random circuits, and then we infer the query with another random circuit, right? Okay, and then at the end of it, we can mitigate the errors in the test circuits. So there are many random circuits, and we train the one, and this is actual data like this one. So when you train, we find out we provide the circuit configuration information to the neural network, and then also we provide the result with calculated errors, right? So result we can come up with the results with the error, right? And then we also estimate the correct answer state, and we can classify the amount of error or characterize the amount of error by comparing with the ideal output and the output with error, right? Okay. So in this way, we can define the amount of errors, and this amount of errors will be used to teach this the learning circuit. And then with another random circuit, we do the same thing, and then we know that what is going to be amount of error, for example. So after inference, the result will be reduced like this one. Okay. So this is what we have done. So we teach the circuit with many different states. Okay, so so what we have to find out is what is going to be amount of error probability for given input and output. Okay, so if we were given with the 111 state for gate circuit U, and then we come up with a certain output state, and if this output state is one of the answer state of the problem, then you will have a strong probability. Or this is an error state, then we're going to have a low probability. So basically, we evaluate all these relations, and then we can define the errors, right? And then error mitigation amount is trained well, in the beginning, we just in the learning state, we just characterize the error amount the produced by the neural network, and then so correction of a compensation term, which is trained by the neural network, and then at the end of it, we just compensate that much of that amount of errors to the final state. So in this way, we can change the probability, okay, of the final state. And the amount of error is estimated with the RMS, and then so this becomes the loss function for the training. And then, so this is how we configured the training network. So in the beginning, at a certain depth position in the circuit, right? We take the input state like this one. So the error state is taken, the error amount is taken at that point, and then after certain number of the gates, we evaluate another the probabilities, okay, and then we also take the output state of that with the error, and then also we provide the information of what was the configuration of the circuit in the middle. And important important informations are number of 1 cubic gates and number of 2 cubic gates. So we just provide a vector given like this one. So this is going to be the input to the training of the ANN, and output is calculated as the amount of compensation. So ANN model is is trained in that way. So basically, this is the model, and the depth was not too deep. Okay, we had only one hidden layer, and then so we, as I discussed before, those are the input states, and then also so this is trained for all possible input states, or all computational input states. Okay. And also this is done for another, and then we investigate two cases. One is the so the upper part shows the configuration of the circuit, and the lower part shows the lower part provides the information about the output states and errors, right? And then one experiment was done with this fully connected input states, input nodes, and the other is done with the subspace learning is provided with these two two separate the handling of the input states, and then the two information are concatenated in the middle, and these two the model was investigated. And then so we trained, and then what we have gotten is at the end of the circuits, we produce the circuits comes with the cross representation of the errors, right? So amplitude damping happens, and also phase damping happens in the state, in the result, and then also depolarization can happen too. And so this is so we use the IBM device model. So IBM the device provides the actual errors, and also IBM KAIST AER provides the error models for each machine. So if you pick up certain machine, then the IBM AER provides the error models for that specific machine. And so we utilize that kind of the model for simulations. And if we just apply the 2-qubit case, we can end up with the improving the errors by or decreasing the errors by 68%, or the for the simple 2-qubit cases with this. So this one comes from the simulations with the error model, and then we can also have did experiment with the experimental devices that shows 39% or 38% of the reductions of errors. Okay, so and this error compensation, provides both the gate error mitigation and the measurement error mitigation together. Okay, so this is a very interesting result. And actually, as a matter of fact, the training is done with the both simulate here. These two results comes with the simulation, the machine, the training with the simulation results, and this comes with the training with the experimental results. Okay, and it worked out wonderfully on both cases. So this one kind of summarizes with more qubits, error mitigation capability with more qubits. We explored the error mitigation capability up to 7 qubits, like here, and then we can see some. So overall, when the number of qubits are small, we can provide a very efficient the error mitigation. However, as the number of qubits increases, the amount of mitigation becomes small. So the complex system, we don't have enough complexity to resolve the problem with the classical machine learning. Probably we can add more hidden layers to overcome this problem. Another approach is scalability. We try to resolve the scalability issue. So we trained the circuit with just simple information like the number of qubit gates only, and the measurement state is not well. In the previous method, we trained the circuit with all possible computational basis. However, we want to introduce a new method, but this is not scalable training. So we want to find out some probability to train the machine with just a local information only. So and the result should be also the local measurement, like just instead of measuring all the computational basis, we just measure the values of qubits. So the previous one has a higher complexity in classical learning, and also it was dealing with only low complexity, but we want to move to this area. That means we want to increase the complexity that we want to handle higher. Okay, and then we want to be able to fix that problem, mitigate the error. So as I just discussed, we just introduced the same type of the ideas, but in this one we introduced some the convolutional neural network design, and then so the gate is fed to the convolutional network. Okay, the configurations, and then The rest of it, we have had the same type of information used here. Okay. And then, so by doing all this kind of design with the convolution network that kind of extracts the information about the gate design, I mean the circuit design, and then we just train with the local area information only, and then we came up with a certain local error information. Okay? So all this the design shows here and how it works, and the result is like this one. With the CNN, we have still pretty good the error mitigation. With the 2-qubit result, it does not show a big difference. However, if we extend the number of qubits, the convolutional, the neural network design uh, uh, is as good as the previously discussed the neural network design. However, the training cost is the train cost of this one was big over to the n. However, train cost of this one was just big over n. So eventually, we and the result was a little bit better with the CNN, even though we trained with a lower number of samples. So altogether, we end up with a certain capability of the uh, the mitigating power of mitigating the errors. So in conclusion, we uh, developed this methodology. That means we are feeding a classical neural network with the quantum information, and in the output we could find the compensation for the mitigation, and then it is a lot more effective than analytical model, which fails on experimental data. However, CNN, ANN mitigate error more efficiently, right? And the both modeling and experiments. One interesting aspect is we train the system with the model based samples, and then we can for specific QPU machine, and we could mitigate the error in of the experimental data of that specific machine. So this is kind of some result that we didn't expect from the beginning. So if I answer to all the discussion that is here, so we were questioned if I can fix the problems of this big guy, but with this this David can say I can give you a hand, okay, because there is some portion that has a polynomial complexity in the error characteristics. This is what we meditate at the moment with our current result. So my presentation ends here. So thank you very much for your attention. And sorry about the very runny discussions, because I just started late and tried to finish it earlier. Okay, so anyway, so if you have any question, I can answer to your question. So somebody loaded a question on the chatting board. Let me see. So this is a discussion about my presentation, or Okay, so Mr. Udai asks to the QPCA. Oh, okay, so I think there's one question from Dr. Suzuki Udai. Okay, so he has two questions. One is how do we get the correct probability distribution when the number of qubits is larger? Um, so that's a fundamental problem that we have. Okay, and then so in order to train the amount of error, we actually calculate the state vector problem, and then so when the machine becomes like 30 qubits something like that, then this one has a still problem. Okay, and so we cannot basically we have to rely on the power of the classical computing machine. So probably this method will be applicable up to 30 qubits system analysis. So I think other mitigation technique tackles the mitigation of some expectation values, while this method works on the mitigation of the probability distribution. This is also the try. Yeah, we were also mitigate the expectation values. Okay, and so what is the motivation you try to mitigate on probability distribution? For example, you find some algorithm where the mitigation of the probability distribution is more meaningful than certain expectation values. Okay. So, well, what I can say for now is, so we are also mitigating the errors in the expectation values, which is the sampling measurement of the output states. So I think in any circuit, we can apply this method. So, of course, in a VQE and quantum, generative adversarial network, both can be, we can use for both the circuits too. It can be an answer to Dr. Uday? Okay, yeah, thank you very much. Okay, so let's conclude the morning session here, morning session in Asia here, and then we're gonna meet, um, uh, you know, uh, after lunches, but actually the time will be a little bit tight. So it is 12:35 in Korea, and we are going to meet at 13:15, which is about 40 minutes later. Okay, so I hope to see you all back in 40 minutes. Thank you very much.